you have the latest stellar addition to maybe stellar astronomy, especially high energy astrophysics, and Craig Heinke from the University of Alberta. He got a PhD instructionally, and after a couple of sojourns in Virginia and Western, he's been in Alberta for a couple of years. And that's a very interesting work using on the composition of these surfaces, and I hope we get there a little bit better.
Great, thanks. Yep. Yeah, so I'm going to talk about what we learned about the atmosphere of the neutron stars, some constraints we have upon their sizes, and upon how they cool through X-ray observations of neutron stars. Two different class stages. So just the brief reminder of the general picture of a neutron star is that they have their supernova explosion. They have mass about, I shouldn't say mass, but now it goes up to 2 times the solar mass. And the exact diameter is uncertain. The interior is thought to be mostly composed of neutrons with maybe some other things in there that give great interest. And there's a lot of physics that we understand now about the crust, which I'm not going to go into focus mostly on the atmosphere material. So just to frame the questions in terms of the physics of that's going on, we understand how the pressure of matter behaves with respect to its density at in the range of atomic nuclei. But when you go up significantly above that, there's significant uncertainties. And here, Globular et al. 2010 have parameterized some of these uncertainties in a couple of density ranges above the range we can actually look at. So we can ask a couple of key questions about this. So one of them is, we know that the interior of neutron stars is mostly neutrons, but it's not all neutrons. There's going to be some amount, at least, of protons, electrons, and muons in there. And we're really interested in one key question is, what is the proton fraction? So there's a symmetry energy. It's basically the chemical potential, the amount of extra energy you get by sticking in an extra proton. We don't know what that is for neutron matter. And so we don't know what the fraction of proton is. So you can say inside the interior of a neutron star, it might be 90% neutrons, or it might be 95% or 85%, and then it's a big difference. They'll show you fairly soon. Another question that we don't know all the details to is whether the protons and neutrons pair up and become superfluids. If the protons do, then they're obviously conductors, so you have a superconductor. And then if that's the case, then the vast majority, 99.999%, of all the superconductors in the world are inside neutron stars. And another question, maybe the most exotic question, is do we have condensates forming of different kinds of unusual particles at high densities in the cores of neutron stars? Do we have pions or kaons, or even a strange quark soup? Do the nucleons dissolve and give you this quark soup? And so one way we can try to parameterize these questions in terms of things we can actually measure observationally, it's not the only way, but it's one interesting way, is by looking at where neutron stars might fall in terms of the mass and the radius. And so this is a plot that you may have seen a number of times before. This is the review article by Lavin and Kosh showing a range of radius for neutron stars and a range of possible masses. And so each one of these black lines, and the green lines are one possible equation of state for neutron stars. The idea is that every neutron star hopefully will lie along just one of these equations of state. They might, so if you have a 1.4 solar mass neutron star, and this is the correct equation, they will lie there. And then if you have a 2 solar mass neutron star like the one we discovered, which is coming out in nature soon, they'll lie there. But there are different possible equations of state. So the idea is if you have a neutron star equation of state which has condensates, which is kaons, pions, and such, then that relieves some of the pressure on the interior because you add another neutron in, you make a little bit more massive neutron star, you can get slightly higher density by having different kinds of objects. Not just all neutrons, you can have these other things. And so then these things, once you get to the point where you start making condensate, the equation becomes much softer and you go down like this. So some of these, for instance, seem to be ruled out now by this sudden discovery of a 2 solar mass neutron star. But there's still a question about where exactly these things peter out. Is 2 solar masses in, or does it go higher? And the key question is, what is the radius? What is the actual pressure in the interior of neutron stars? So we see neutron stars in a number of different manifestations. The ones which are by far the most numerous and probably the most anticipated of them altogether are those where we're seeing there's some manifestation of the behavior of the magnetic field of the neutron star, including the radial pulsars and the magnetars. And I'm actually not going to talk about those so much in this talk. I'm going to talk about the other two. So in one case, for neutron stars that are very, very young, we may be seeing principally the X-rays are just black body-like emission from the surface of a very young neutron star, just heated up in the supernova that created it, and we're just watching that thing cool down. So here's a supernova remnant, Cas A, and there's the neutron star that's centered, the Rosetta. And then the other scenario is where you have a neutron star that is engaging in accretion and certainly tail off the companion star. And for instance, I like to study these things when they're actually not accreting at that moment, but in between times when there's been substantial accretion. And then you can see the neutron star surface directly. So these are what we call transient X-ray binaries, and this is very, very raw data in the Rossian X-ray Timing Explorer from its all-sky monitor, showing the behavior of one of these objects. Actually, wait, let's talk about more relatively soon. So all the red points here are data that are within 3 sigma of 0, so they're non-detections of this object, and the black points are more than 3 sigma. And you may note that there are some red points that are even higher than many of these black points, particularly around these gaps here. And those are the gaps when the sun goes close enough to this object that the RXT all-sky monitor can't really separate it out, and so the uncertainty becomes very large. But so you can see there have been multiple different outbursts of this system over this time frame. And in between the outbursts, we think that basically the system is just re-radiating the heat that it was dumped into the surface during these outbursts. And this is an example of one of these outbursts, a fairly rapid rise in exponential decay as the disk dumps all the matter onto the neutron star. So when these things are in their outburst state, when there's a lot of matter falling down from the neutron star, then you have strong emission from the disk of the neutron star, and the emission from the neutron surface is heavily Comptonized, up forming at hundreds of keV in some cases. And so in this case, it's very, very hard to figure out the details of what's going on beneath our surface. And I make no attempt to try to model what's going on here. I say, okay, there's a lot of astrophysics going on here that doesn't relate to the interiors of neutron stars. So I'm interested instead in the quiescent parts of this. So this is the luminosity of one particular transient, Aquila X1, as seen over an outburst in about 2000, and then dropping down to quiescence. So the quiescent luminosity is not exactly stable. There seems to be possibly multiple components here, but it's much closer to stable than outburst.
Is there anything new in the last year or two on the non-thermal component of this quiescent flux, which is seen in some sources?
There is. Let me go to the next slide and address that point. So here's the. This is the I'm going to show up the non-thermal flux. So here's the thing, right? There are 2 components that you see in these low-mass X-ray binaries of neutron stars and zero neutrons. There's only one for the black holes because this component doesn't exist in a black hole. That's the radiation from the surface of the neutron star. So this is a black body-like radiation. The way in which it's plotted here by Rutledge, it looks like the model and the data don't agree, but they do. It's just that in this model, he's unfolded to remove the NH, right? So the absorption at lower energies. But there's a component here, and then there's this other component here. We don't know what this is. We would really like to know. NuSTAR may be able to tell us, because here's the thing, right? Well, we only have we don't have a full decade of information here. We only have a few data points, and we would love to see, does this have any curvature to it or anything? This fit with the power law, because this thing is still dominating up to here, so we only have a couple bins. If we could go out several more bins this way, that would be wonderful. And so we might be able to do that with NuSTAR for a few of these sources. So we don't know what this is. There are suggestions that, in some cases at least, it's probably related to continuing accretion onto the neutron star. There's a reasonably good argument for that from XTE, I forget the name, it's the transient Z source. Although I should say now the first transient Z source. There's now a second transient Z source. It's going off this week. But that's in Turzin 5. It's quite constant. Anyway, that object, so basically the point was that when we put it in the terms of this part here seems generally to be stable, but not always. There have been systems where the temperature of this seems to vary quickly on short time scales, and that's always the case when this is also relatively strong. So that would tend to indicate that if you have accretion here, that might also be affecting what the temperature of the neutron star surface is. In cases where this thing is absent, these things seem to be relatively calm. I'll show you the details of that in a moment. There are also cases, such as SAX J1808, which I'll tell you more about in a minute as well, wherein the power law component seems to dominate. It's hard to find this thing. And in many of these cases, the total luminosity of this is quite small. And this power law component might be referring not to actual continued accretion, but perhaps instead to a radio pulsar synchrotron X-ray emission. It's thought that some of these things may, in their quiescent frame, be actually turning on as radio pulsars. And in that case, you might expect a pulsar wind nebula, which has something like that. This is still unclear, and we'd love to know more about how this thing behaves. Okay. Is there a water fountain real close?
Probably channel that.
Okay, so let's say you're interested in that black body-like emission. It's not pure black body, and the reason is the actual opacity of the material on the neutron surface is not constant with the energy. So if you look at the opacity with energy for different possible compositions of neutron surfaces, you find a newton to the -3 dependence of the opacity, which is the Thomson scattering and Thomson absorption, in both hydrogen, helium, and free absorption, yes. Yes, and this is so in more complicated atmosphere, you have all kinds of lines and such. So what does this mean in terms of actually looking at the atmosphere? Does?
Sorry. Question. What's setting the scale for when magnetic fields become important?
Depends on when the magnetic field strongly adjusts the energy of the transition.
10 to the 9 is basically when the cyclotron energy equals the binding energy of hydrogen.
10 to the 9 goes?
Yeah, few times.
Almost square times.
So if you're below that, magnetic fields are relatively unimportant. Now, the nice thing about everything I'm talking about with these quiescent LMXB binaries is that in all these, we think the magnetic fields are relatively low. We know their descendants, the millisecond radio pulsars, which are oftentimes having the same spin periods, also show very, very low magnetic fields. And some of these, we actually have direct constraints upon the magnetic fields through looking at for spin down and looking at when the propeller effect turns on, which I won't go into great detail. So let's say that we're pretty confident these guys are low magnetic field neutron stars. So these are different models from Zappel in 1996 about how the different atmospheres behave. So just take one random example, say this one here. Here's your black body spectrum. And then for that same temperature, what do you get if you have a hydrogen or helium atmosphere, which are these two lines here, versus an iron atmosphere. The iron atmosphere has all kinds of lines. It's basically similar in terms of where the major part of the spectral element is. But the hydrogen and helium atmospheres, because that frequency-dependent opacity, put out significantly more of their energy to higher energy, more of their flux out to higher energies. So it puts it more into the X-ray. And the consequence of this is if you try to fit these things, the black body, without realizing that it's actually a changed atmosphere, you'll get a radius that's too small. So if on the other hand, you try to fit these things, say, set next to or fill next to one, these kind of guys, with models that include the hydrogen atmosphere, then you get inferred radii that are in the range of about 10 kilometers. We have a good reason to think that in anything where we know the companion is a normal star, in equivalent quantum where we have some idea of what these things are, and we know the companions are, in fact, main sequence or subgiant, this kind of thing, but not white dwarf stars, that you will have hydrogen in increasing matter. And that atmosphere will stratify within about 10 seconds. You will definitely have hydrogen on the surface. And so if you know the hydrogen, you know the magnetic field, you can very easily pick the spectrum. And so that means you have a pretty good constraint then, and with radius over the distances. You can directly measure R over D. You can measure the flux you see, and you can measure the temperature. The problem with most of these things is the distance is relatively poorly done. So let's say you'd like to find out what neutron stars are made of. One of the things you would like to do is to put some constraint upon the radius. so you wanted something where you know the distance. And so this is where globular clusters came in. This is an idea that Ed Brown and Bob Rutledge originally had. To say, let's look at some of the globular clusters which have neutron stars in them, and actually measure the radius there. So this is possibly one of the best examples of this. The globular cluster 47 Tuc, Southern Hemisphere. Anybody who goes down to the Southern Hemisphere to go observing should just step outside tonight and look at it. It's great. It's near the Small Magellan Cloud. This is in an X-ray. You can't see stepping outside the telescope, but also looks quite nice. These two are very bright quiescent low mass X-ray binaries. This one is unfortunately unsuitable for use because it's edge-on, eclipsing, and the NH is continually changing because they're looking to the accretion test. But this one is not. It's perfect for this field. Perfect for these studies. So here's the spectra of this object, X7 and 47 Tuc. There's 4 different spectra because there are 2 different observations, each of which took part of the observation in a normal CCD mode and part of it in a mode designed to reduce the amount of pileup. Pileup is when you have multiple photons landing on the detector on the same or adjacent pixels during one frame time. So they're regarded by the instrumentation as a single photon with the energy that's combined in the two. That can mess up your spectrum. We have to model for it, and it's useful to have it check on. So these are your ones that don't have pileup, and these are the ones which have more photons, but you have to model pileup. But so the nice thing is you fit this to the hydrogen atmosphere, and here's your residuals, which have basically there's a feature here which is an instrumental feature in the Chandler's fog. But there's no evidence out here of that power law component. That's very nice. It suggests that there's not continuing accretion going on, and it makes it much easier to try to model the spectrum if you don't have a sector quantum there. We can strongly constrain any variability on timescales between hours up to months, and in the multiple years between these two nature effects, to less than 4%. And that also is indicating there's no significant accretion going on. So all this makes us think that we could probably be fairly confident in saying that if there's no accretion, there's no other elements being dumped onto the neutron star surface over time scales of 10 seconds or so and change the opacity. So we can say it's all hydrogen. And so we have an excellent fit. So then what do you get then in terms of constraints? So I said that you'd be trying to constrain the radius. There's a degeneracy there because in addition to just the size, the other thing which will affect the temperature is gravitational redshift. And so what you end up with is you end up with a constraint in some combination of mass and redshift, mass and radius. So the simplest thing would just be lines that go like this, R infinity. It's a little teeny more complicated than that because if you change the surface gravity, which depends not exactly the same way as the redshift, then that will change slightly the atmospheric structure. So we get these constraints. So these are 1 sigma and 90% and 99% contours enclosing where we think the X7 neutron star lies. And then these are sample equations of state. So the canonical values, 1.4 solar masses and 10 kilometers, lies there, well outside the 99% confidence contour of this region. So that's nice. It means there's something interesting going on. Either the neutron star is relatively heavy, or it's relatively large in radius. Now, given the information we have in the past few weeks or so about there being found a relatively large mass neutron star, you might tend to lean towards a high neutron star, but I will caution you that I don't think this is the explanation. This guy is one of the brightest objects in 47 Tuc, and is actually one of the most luminous quiescent low mass X-ray binaries that we've seen anywhere in any globular cluster or anywhere else. We have, as I'll give you a reason to understand in a few minutes, reason to believe that the more massive a neutron star is, the faster it will cool. And thus a really, really X-ray luminous quiescent neutron star probably is going to be a relatively low mass star. So for that reason, if I had to bet, I would say that it's more likely to be a relatively large radius neutron star than to be a high mass neutron star. Now, this is not the only neutron star for which this kind of work has been done. So here's the same constraints of X7, the 90% and 99% confidence contours. So 90% is the shaded thing, and 99% is these outer redlands here. Comparing with the most interesting other measurement, which is one in globular cluster M13. Here's its 90% confidence contour, and it's 99% comes up here. So at the 90% confidence range, these guys don't overlap. 99% they do. So you have a couple different possibilities. You could either say, well, the 90% confidence contours are a little bit incorrect by some means or other. And there are systematic errors one could point to in either of these different observations. You could say that maybe it's one of these equations of state that lies both in here and over here. Or over here and over here. Or you could say that maybe this one here is actually not the same atmospheric composition as this one. So I talked about different kinds of atmospheres, hydrogen, helium, and so on. And I said if you have a neutron star that's accreting from a normal star, it will always have a hydrogen atmosphere. But what if it's accreting not from a normal star, but rather from a white dwarf? In that case, it's possible that all the material that accretes on the neutron star, maybe all helium or maybe all carbon, depending on what kind of a white dwarf it is. And so you may end up with an atmosphere that's just helium or carbon. And so I approached then Win Ho and said, look, I think that if we tried a helium or a carbon atmosphere, it would probably change the exact location of these contours. We might shift these positively outwards. We have reason to think that the helium atmosphere is a little bit harder than the hydrogen atmosphere, and so we might shift these outwards. Could it explain the discrepancy perhaps? So that's how we started working on helium and carbon atmosphere. And I'll come back to this in a little bit of talk. But I want to talk about one more topic then, with cooling of these low mass electrons. So the cooling of neutron stars, I think, is dominated by neutrino emission. And there are many different ways in which neutron stars can emit large quantities of neutrinos. The simplest way is through direct ERCA. If you have the fraction of protons inside a neutron star is high enough, there can be the simple direct interchange. That you could have neutrons changing into proton plus electron neutrino, or protons like capturing electrons into neutron plus neutrino. These things can happen without any other bystander particles being involved. And if that's the case, these neutrinos and antineutrinos just run right out of the star, fly out into the infinity, and take away a significant amount of energy. And so you have very rapid cooling of the neutrons. If the percentage of protons isn't that high, you can still have what we call modified ERCA. It requires a 3 nucleon interaction. So it's slower, but it still does the same basic thing. Alternatively, if you have condensates of kaons and pions, then you can have ERCA-like reactions where you have neutrons re-rate their quarks and produce other things. Now, all these different mechanisms of ERCA are suppressed if the particles are superfluid, bonded in pairs. So this is a schematic idea in Yakubov and Petek about the general idea about how you might have a range of different cooling rates for different neutron stars. So down here is density, and then versus the amount of heat lost by the neutrino emission. So let's say you have a neutron star which is relatively low mass. And that means the density at its center is relatively low. So it reaches up to somewhere here. In that case, it's only able to access this relatively slow neutron-neutron Bremsstrahlung emission, assuming that it's superfluid throughout. At some high density, though, the superfluidity is suppressed. And if it's suppressed, you're able to access ERCA reaction. Now, which ERCA reaction you access depends upon the interior of the neutron star. But let's say you have a relatively high density neutron star, and it has kaons in it, you'll then go up to this. And so then the difference between a high mass neutron star and a low mass neutron star will be this range in cooling rates. If there are pions, you get a higher rate of cooling. And if it's nucleon direct ERCA, you get the highest rates. Hyperons actually use the rate. So you expect then over a range of massive neutron stars to have a range of cooling, and you might be able to get one of these different ranges. So this is examples of possible superfluidity temperature curves, such that it goes with density and temperature, and if you go above some density, the superfluidity dies off, and you can maybe access ERCA things. If you go, that's for a given temperature. If you're above these, which is this is very, very high temperatures, very early in life, the neutron star, then the superfluidity is negative. Once you go below it, the superfluidity turns on. Once you cross one of these superfluidity lines, there's also another mechanism of cooling that relates to the formation and breaking, principally the formation of the Cooper pairs that produces neutrino emission. And the breaking of it takes away energy, but that's all. So what this is saying then is that there's another way which as the neutron star drops below some point when it accesses, say, neutron superfluidity, if this one may be something that gives you a lot more rapid cooling than proton superfluidity, you can have a sudden temperature drop at that point. And I'll come back to this as well. So these are possible cooling curves for young neutron stars, showing this example of a quick temperature drop. So if you have that temperature, if that heat temperature is about here, and you have different neutron stars with different masses cooling at different rates, they reach us at different points, and each of them has a sudden kink in their curve. We need to have some kind of a range of cooling rates in order to explain the range of neutron star temperatures at a given age, which have quite some range. So there's something going on. It's not absolutely certain that there's some Urca mechanisms going on. You can get some range by, say, changing the thickness of the envelope, or just by having superfluidity changes. These young neutron stars, then, are not a really wonderful test, then, of comparing the, whether there's some Urca mechanisms going on.
How much uncertainty is there in the relation between the surface temperature and the
interior temperature? Yeah, there's a kind of, it depends on,
depending upon atmosphere.
It's not so much, well, so the atmosphere is a factor because the actual surface temperature is not what you measure. You measure some color temperature, right? And then there's a relation between that and the actual surface temperature. That's one thing. And that depends on your atmosphere. So the black light is the higher temperature. The other thing is that underneath the atmosphere, the most heat insulating part of the star is the envelope. And if that's made out of iron, it has one conduction level. And if it's made out of lighter elements like carbon, it's a lot slower to conduct heat. And so that gives you a distinct variation in where the curves are going, which I'm not showing you. This is an example here. Is that a good answer to the question?
I guess I would like to know quantitatively. I mean, you measure the photospheric.
Yeah.
And you're trying to draw some conclusion about the interior.
That's right.
And so I was wondering how much lower is the atmospheric temperature than the interior temperature? The typical model.
There's it's about, I think it's on the order of 100, if I recall correctly. If you have 10 to the 6 temperature, 10 to the 6 Kelvin atmospheric surface temperature, then your implied interior temperature is like 10 to the 8 Kelvin. Still seems to be non-exact.
Yeah, and then if you change from carbon,
it gives you a range. It's not a factor of 10. So as I recall, there's a paper by Danny Page where he tries to explain the range among young neutron stars mostly through varying the envelope. So you assume that you know whether it's hydrogen atmosphere or what. Assuming that these guys are all hydrogen, and then you can get this range here. So that's a factor of, not quite a factor of 3, it can be a factor of 2 or so, from varying the envelope, whether you choose a carbon envelope, lighter envelope, versus an iron envelope. I think that's the kind of range that is important.
Well, you also care about the depth of the light element. Right.
Yeah. Well, if you have the light element is very small, then yeah. So you could increase the depth of that. So the iron is.
Let me just follow up on one thing. So when you're talking about the envelope, is this the region in which you think that the composition is just the accretion of the material, or do you think this is the region in which you have to worry about whether you're entering this equilibrium or not? In other words, whether the density is high enough so that you imagine that nuclear reactions will already control the composition.
Good question. This is the envelope we're talking about is the region that's above the part where the nuclear reaction.
And this is a place that depends on initial conditions.
Yes, that's right. Initial conditions, or there may be some effects going on, but it's not an area where we're doing significant thickened nuclear reactions. That's below the R limit. So this is just an illustration of applying those possible different Urca and Urca-like mechanisms to the standard cooling. So here's your neutron-neutron Brownston cooling curve. And here it is with, let's say you have chaotic condensates in the center, and at a certain density threshold, you can allow those to engage in Urca mechanisms. You can get this range. If it's pion condensation center, you get this range. If it's nucleon director, you get this range. So obviously, from the data you have so far, you can't rule out that it's just this, or even just to say that it's just differences in the envelope. So that doesn't tell you too much yet. So now, part of the problem is that, let's say you want to find something way down here, but how do we find these young neutron stars? Either they're pulsars, in which case there's also non-thermal emission, typically quite strong, and then you can't actually, well, so look at these guys. These guys are cases, there's a crab, and here's 3C58. Typical pulsars where there's strong non-thermal emission, and you can only put an upper limit on the neutron star thermal emission. Now, you could be toast, we could try to go down. What about some systems where there's, this is one in Cas A, if I recall correctly, where there's no evidence of a pulsar. So then you're looking for something which is just a hot, thermally emitting black body-like thing inside a supernova ring. So then you have to find these in your X-ray observations. If it's really cold, you may not find anything at all. So David Kaplan, for instance, has went looking inside several supernova rings where no central compact object, as these things are done. We'll talk about it more in a bit. By no pulsars are known, and he puts limits down here, but he doesn't know if those are actually, if there's actually a neutron star there at all, which is really cold, or if it's a black hole, or if there's just no neutron. So it's very difficult to do it in this frame of reference to look for this. So this is one reason to go and look for back at the transient systems. In these guys, we know that there's an X-ray binary there, and then if it's a transient system, we can look when it's off and look and see if there's a thermal component. So this one's a beautiful one to do because, well, for one thing, we know a lot of things about the system. We know we see pulsations from it when it's accreting, and so that tells us that we can figure out what the orbit is and such, and we can actually get an estimate of the magnetic field. So I took detailed spectra with XMM hidden with this, and this is the convolved spectrum that the instrument responds. So it doesn't look like it, but it fits perfectly with the power level. So there's no evidence of the neutron star surface there at all. This is all that other thing. We don't know what that thing is. Maybe it's pulsar wind nebula, maybe it's accretion, but it's just that. These are the maximum you can get from the thermal component. And this is essentially, I think, the strongest limits on the neutron star luminosity we have yet. Less than 6 × 10⁻³ meters per second for that. So where does that put us? So here's another frame of reference we can look at, the cooling of neutron stars. So in this case, instead of looking at temperature versus time, we're going to look at temperature versus accretion rate, time average accretion rate. So if you integrate up over the amount of matter that's been dumped onto the neutron star over a long period of time, you can figure out the time average accretion rate. So for instance, Quilex 1 is here, for instance. And this here is your standard cooling track in Bremsstrahlung. So then you would interpret that, okay, so Quilex 1 doesn't seem to have any of these strong neutrino cooling factors going on. And there's other systems, many of these are double number limits and things like that, but there's systems where you actually measure and say, okay, it's significantly away from this track. And then here, the saturation rate. And it seems to be definitely below this one here. Here's the top. So that seems to rule out either of these two, and you can't get far enough down just by changing the envelope. So this indicates that probably we're looking at direct proton ERCA or hyperon ERCA. And actually, I can't rule out strange quark mapping things. Those things, there are a lot of parameters to play with in those models. And this one here is the one that Peter Yonker studied in great detail, 1H1905+000, where we spent 300 kiloseconds of Chandra time and only detected one photon in the air circle. So it gives you a very nice idea. So these two here are giving us strong indications that there is some really, really efficient neutrino cooling in some neutron stars. Probably either direct proton or
Like you say that your envelope for 1808 is very secure, because that would be the other, right? This is really very low.
Yeah, yeah. So for this one we don't know because there's only one outburst. For this one, on the other hand, it goes off every 2 years. That's a very nice feature because you can see it coming every 2 years. It's always about the same flux. So unless there's something changing on longer time that we don't know about, the m dot is quite secure.
But what time scale do you need this on? So but theoretically,
well, theoretically, the theoretical time scale we want it on is 10 to the 5 years.
Okay, so it's long.
So really long. It's not a grad student project. But what we have access to is 15, 20 years.
Let me understand what you measure. So when you have one of these outbursts, you think you're capturing volumetric luminosity, and that's where you get the mass transfer rate.
Yeah, that's right.
And then when you look at the long-term luminosity, it's some black body or some atmospheric.
Yeah, hydrogen atmosphere for these guys. That's what we're measuring. So now I want to change gears a little bit, talk about very young neutron stars, get back to where those helium and carbon atmospheres turned out to be useful. Then I'll come back again to the cooling and this as well. So among the young neutron stars are those that are from radio pulsars. The crowd is the most obvious example. And then there are these things called central compact objects, just actually point sources inside supernovas. And most of them show black body-like spectra and relatively little long-term variability. And so we think that these guys are probably neutron stars, but not radio pulsars. So there's an example of one of their X-ray spectra. This is from the Vela Junior central compact object. And they have no optical radio or IR counterparts, so we think that they're actually single neutron stars, not binaries. So the most exotic in some ways of these is the Cas A central compact object, which is the youngest known supernova that has a central object in the center. This is discovered in, not in this image, this is a later Chandra image, but in the discovery, but in Chandra's first light image in 1999. So that means this is probably the youngest known neutron star. The first question you can ask is this object a pulsar? So this is one of the early papers looking at the point spread function and seeing it's consistent with the Chandra point spread function at that location. Whereas if you look at young neutron stars that are radio pulsars, they often show this pulsar wind nebula. And of course, have no radio pulsation. So then when people started looking at the spectrum of Cas A, they found, okay, it looks kind of black body-like, but the inferred radius of that black body is only 0.3 kilometers, which is a little bit small to have for a pulsar cap, for a pulsar polar cap, which might be one reason you might expect to see a small portion of the surface be heated. And B, you don't see pulsation here. So this is an example of what you might expect if you have a neutron star where the entirety of the surface is emitting, and then you have a hot polar cap plus a non-thermal component. This is a phase-all spectrum of a radio pulsar. Let me just run the once more so you can see how you expect to clearly see pulsations as this thing moves around. For most viewing geometries, you can contrive viewing geometries where you won't see this. If, for instance, the hot spots are aligned with the pole, or the pole is aligned with the line of sight, but it requires some hard work. So then people have, a number of people have looked very carefully for pulsations from Cas A. It's very tough to do anything other than Chandra, and Chandra is not always the best thing for looking for pulsations. But the constraints are now at around the 10% level. And I think Gotthelf and Halpern are looking to do even deeper, trying to prove me wrong. So we'll see if they're there. They would like to show this is actually pulsations rather than the solution.
Can you rule out all multiple frequencies of rotation?
Well, no, but these are the constraints that we have so far. Right? So down to 10 to the minus 3 hertz you can do, and you got this from
difficult on fast rotation.
So there's really fast rotation.
Now this is from Variability 2002 with XMM. There are the Chandra ones from Halpern et al. 2010 use the high resolution camera on Chandra, which has extremely fast recording capability. And I think it's microseconds.
So then they fold it with all different periods.
That's right. Yeah. You don't have to worry about acceleration searches here because you know it's not in a binary system. So you're just looking for periodicity. So what are the different possibilities for explaining what's going on in this aspect? So if you fit with the hydrogen atmosphere, which Pavlov and Luna have done, you do get a good fit. But the inferred radius is only 5 kilometers. If you accept that there's no pulsations, that means you're seeing it from the entire surface. Well, this is the kind of constraint you get in mass radius space. Okay. So then you're in this little range. So that's a little bit of a problem because normal neutron star equations of state are going like up here somewhere, right? The only neutron star equations that you can get that come through this portion are strange quark matter stars. So you could have this be tiny little strange quark stars at about 0.3 solar masses and 5 kilometers. But I don't think there are any supernova modelers who say that you're going to produce these things in supernovae. Now, not to mention the fact that I would require a lot of evidence for, I believe, a strange quark star that was this kind of size and mass. So it's possible, but it seems unlikely. And then this is Pavlov and Luminous modeling for if you have hydrogen hotspot. This is their black body effect, and here is your hydrogen atmosphere effect. So you can see the hydrogen atmosphere gives you a slightly broader and harder thing for one component than the black body does, but they still needed the second component to get the highest energy stack. And then, so this one here then matches the whole neutron star surface, but this one here is getting this big. And you should see pulsations here, and you don't. So that was their best explanation, was it's just unlucky. But then Win-Ho and I had another thought, let's try some alternative atmospheres. Let's go after these helium and carbon atmospheres that Win-Ho is making up, and see if they might explain this one. So these are the different kinds of atmospheres that Win-Ho made. Here's your black body atmosphere, and these are just different ones at the same temperature. So there's your hydrogen and helium atmospheres, and then you can see if you look at the oxygen, iron, and nitrogen ones, those ones all have strong lines. Right? Here's your oxygen one that's got this, or huge features in some cases, which can be ruled out by trying to fit it with, say, these spectra there, which are quite smooth. The only one which made a significant difference to the overall spectral fit in terms of getting the radius up to where we might like it, and didn't provide any spectral features in this ballpark here, which is what we measured, is this carbon atmosphere here. Slightly harder than the hydrogen and helium atmospheres, no features until you get down to about 0.35 or so KUV, a little bit lower when it's redshifted, and the problem with trying to find that on Cas A is that this thing is behind a huge amount of gas and dust, so it cuts off all the flux below a little over 1 KUV. But we can't test it, unfortunately, which could be seen as a blessing, so kind of weak result. But, so that's the carbon atmosphere is the one that seems to give a good explanation. Gives an excellent fit to the data, slightly better fit than the hydrogen or helium atmospheres, and gives you a radius that's about 10 to 12 kilometers. So it seems to explain all the data very easily. Now you might ask yourself, why would you find a carbon atmosphere on a neutron star? Why would you find a carbon atmosphere on a neutron star?
Is there a simple explanation why quantity inside our spectrum than hydrogen?
That's an opacity question.
Yeah, basically this ionization edge. If you see an edge in the spectrum, and that's 0.3 kV, that takes out a lot of flux and has to go somewhere else.
Oh, I see, okay.
Yeah, okay, so it's the flux that comes out here,
Right.
comes out there.
That's right.
Are these are non-LP models? Where you're,
They're LP.
They're LP?
Yeah.
Oh.
Any other question? So the key question, and this is where the chain comes in, is why would you have a carbon atmosphere? The first thing which we thought of was maybe it just depends on where you have the mass cut, what portion of the neutron star falls back and what portion of it is ejected. But the problem is that you're never going to get the mass cut to be in the hydrogen regime to explain many other neutron stars that are older than this. So that doesn't explain it. But you do expect that in the interior of a neutron star, in the interior of a supernova explosion, you're going to have all kinds of gamma rays going around it, spalating things, making protons and alpha particles flying around. So you should expect those in all neutron stars. Why would you not have them in the youngest neutron stars? So Phil Chang has an argument that goes like this. It was originally for the older neutron stars and was applying it to hydrogen and saying, look, let's say you have a neutron star where the hydrogen is on the surface, and up on the surface, it's not hot enough to burn the hydrogen, but if you go deeper down into the neutron star interior, there's a burning layer somewhere down there where the temperature does get hot enough to burn hydrogen. And some quantity of the hydrogen is continually diffusing down. So this here would be basically the fraction of hydrogen coming down like this. And some little bit of it comes down here and is burned away. And then some more has to diffuse in, replace that, and that gets burned away. And over a long period of time, you can burn away all the hydrogen in a focus group. And it turns out that that works great for old atmospheres. It also works for young neutron stars. And for young neutron stars, you can also burn away not just the hydrogen layer, but also the helium layer. And so you might end up with just a carbon layer on the surface. So now why would you then have hydrogen in older neutron stars? The argument then would be that maybe there is continuing accretion, a little bit of fallback in the supernova remnant during the entire few thousand years or so that we see these guys, and that in the first few hundred or thousand years, all that hydrogen helium is burned away, and then once the neutron star gets cold enough, it can no longer do that burning away, and then you reaccumulate the hydrogen in the helium. An alternative possibility, which Pulsations was talking about at lunch, is that perhaps you get rid of this and you don't accrete anything more, but if it's a radio pulsar, then you've got the positrons and electrons from the magnetic poles slamming into the surface and possibly breaking apart some of the carbon and constituting helium or hydrogen. And we can do that. So in either case, there are ways you can reproduce the hydrogen and helium atmosphere. So now if we take this, the carbon atmosphere that we've got and we know actually the distance to Cas A. The reason we know it very well is because we can actually, not me, but other people can, measure the expansion of the remnant in the two-dimensional plane this way, and also measure the radial velocity of material coming toward this remnant. So you have a geometrical argument as to the distance of this object, about 3.4 kiloparsecs. So then you can then use the same model, the same rationale we talked about before, to try to measure what is the range of mass and radius there. And so this is your 1 sigma 90%, 99% conference contours for this atmosphere. And then these are 3 sample equations to state in the blue region is kind of roughly ballparky what people think might be reasonable. Now, I should say, don't take this one quite as seriously as the 47 type results, because there's 2 uncertainties in here. One is that we don't really know the atmosphere composition. I mean, we say carbon fits, but there might be some amount of helium in there or some amount of something else. The other thing is that we also don't know the magnetic field terribly well. And as you crank up the magnetic field, that changes the opacity structure of the atmosphere. And so that will change then where in M and R space you land. But this seems to be reasonably consistent. That's what you might expect for a neutron star.
If you crank up the magnetic field, you're a lot more to get pulsations.
Yes.
It's hard to make isotropic.
That's true. But you have there's some range to play around.
We have things like 1856, which is a 10 to the 13,000 magnetic field and 1% pulsation.
Yeah, and that could be just a geometrical effect. It could be that it's well aligned. And actually, that's something I should mention here, that there could be pulsations here that are below our detection threshold. There can be inhomogeneities on the neutron star surface. So there's many different things. Just you have to have those be very small or be
one thing that I think really helps polar caps, but if you have a magnetic field, it just makes them bigger spots. It's easier to hide them.
Yeah.
But yeah, the line rotator then doesn't possibly bring back the pulsar even and
Yeah.
then you would naturally pulsar.
Yeah, I mean, the hydrogen model is a possibility.
It certainly is, yeah. The carbon model is lovely, but we can't prove it to be sure. So, at the moment it seems to be consistent with everything and gives us interesting results also for cooling, which I'll show you. So this is where Cas A, if you believe that this is a carbon atmosphere, what the temperature is that you derive, and it's right smack in the middle of the range of different temperatures for other young neutron stars. So it doesn't give you a huge amount of information just by itself. Because you can still play around with a bunch of different parameters to get this range. Then comes the next interesting. As we looked at these different observations of Cas A, people have looked at the Cas A supernova remnant on and off for about 10 years. And so we have quite a substantial amount of data. So if we look at all the data. Some of the data, unfortunately, has bad columns that run right across the central compact object. And the first processing we had of that, we said, oh, look, there's a rapid change right there. Then we realized the bad columns were there, threw those out. But even if you ignore those, data, there's still some evidence of variability in all the better calibrated data. So this is a series of observations with different colors for this thing. And I've got the same model going through it all. This one here is taken into mode to reduce pi-off, so that's why it looks higher than the others. So these are the different models here, all about the same. And then here are the residuals. And the residuals are the interesting thing. Right? The black and the red ones are the earliest observations. And the blue and purple, you can kind of see the cyan here are later observations. The interesting thing is the residuals are shifted significantly. The earlier observations have significantly higher residuals, and the later ones significantly lower residuals. And it's spectrally fairly uniform on the whole thing. Now, there's a lot of different possible calibration issues with Chandra. One of them is that there's this contaminant that's accumulating on the ACES camera. And that tends to cut out low energy photons exclusively. There's charge transfer inefficiency, which is decreasing over time. That tends to change the low energy photons. So, in all my talks with the Chandra people, at the Chandra X-ray Center, they can't think of anything that will change the entire effective area of Chandra over this 10-year period. So this leads us to think that it's actually a change in the actual temperature of the neutron star itself, which at first order releases a significant change of the density. So this is what we get if we take this interpretation, that we now have evidence of the Cas A neutron star cooling. The purple ones here are those other ones, which this series here are the ones that are affected by the bad column line process. But these ones here are the well-calibrated observations. They show the temperature dropping by 4% over 10 years. If this is right, it is the first time we've actually measured the cooling of a young neutron star. And that is a really interesting constraint on cooling models. So this is the last slide with serious information on it. Here is one set of cooling models that goes through this at the right dt, right, the temperature with time, compared to the other different objects here. So this would indicate you have to, the thing is you have to get a relatively steep decrease here compared to what the overall decrease over the entire thing is. This is work that Peter Stern and al. is doing, trying to map this. And it looks like you need to have neutron superfluidity turning on relatively recently.
What's the burning temperature?
Sorry?
What's the burning temperature?
Well, it's, I don't know if it's
Probably it's lower than 29.
Yes, it looks like, I'm guessing it should be on the order of 210 dA or something like that.
210.
That's my guess by looking at this being C 210 to 6 and thinking it's around 500 more. So obviously, you know, there's uncertainty.
Oh, well, yeah, totally. So, you know, you can, parenthetically, you can explain the lifetime expectancy of magnetars. There's delay in the superfluid transition.
Okay.
You do magnetic heat. It works quite nicely. I worked there a few years ago. The carrying temperature about 5, 6 times 10 days.
Okay. We should talk about that a little bit more. So anyway, so that let me finish up. I think I'm a little time. So that's it. That's the summary of the Cas A results, and this is the summary of the different kinds of things that these kind of neutron star observations do. And thank you very much.
Well, thanks, and there'll be tea and cookies up